Hey, timer startup. How's your day going? Oh, my jaw. Okay, so let's try that again. How is your day going?
Good. How's yours?
Ah, doing okay. I found an example right before class started about in sort of crops and growing corn. So I thought maybe I'll bring that one for class. We'll find out. We'll see what happens. Yeah, so we're getting towards the end of the term. This 5-week summer term is fun in lots of ways, but I think I know this stuff and I feel overwhelmed as though I'm constantly sort of dealing with preparing or et cetera for class. I can understand being in your position, learning the stuff that's also got to be a challenge. But you know what? That's why you signed up, to learn it, to pass it, something like that. Let's focus on maybe what we need to do before the end of the term. And I'm going to try and share a screen with y'all. That's not really focusing on what we're going to be doing for the rest of the term, but that's just today. If I was going into, okay, come on. Maybe I'll go into student view so that I show you stuff that is looking different than you normally see it. If we're looking at what we're supposed to get done during the whole of the term, we are really close to the end. And today is chapter 10. And tomorrow is 11. And then we'll see what happens on Wednesday. And where it says chapter 10/variable selection, I probably should not have written it that way. I should have written chapter 10 model selection and chapter 11 variable and model selection. Essentially, today is, what if we have an experiment that we've done and we need to analyze data from that experiment? And one of the factors in the experiment was, well, quantitative. I guess I could have, 3 different varieties of broccoli. Sure, no problem. But what if I gave them 4 different levels of water? Water level 10, let's go with gallons per 10 square feet per week. Okay. And then we could go with 20, 40, and 80. Okay. So we could have different quantitative levels. And there's a real benefit of not just fitting these variables as factors in the way that we had so far, categorical factors. We might be able to do something else and be better off for it. So that's today. Tomorrow's chapter 11. So suppose we got to pick some variables to form a model. Which ones should we choose? And then hopefully Wednesday we'll be doing something with logistic regression, which is, yeah, we've been doing regression for a long time now. What if your response variable is either a success or a failure? Rather than measuring a numeric outcome, if the outcome in logistic regression is a yes or a no, a living or a dead, something like that. The model is not much different than what we've been doing so far, but there's a couple subtle differences that would be worth mentioning. But because the logistic regression is not dramatically different from stuff we've already done, it seems like a great thing to do to finish our term up, because it doesn't push y'all overly much in terms of learning new content before the exam, but it still is learning something beneficial. Okay. So that's this week's plan. And let me just mention the final exam. If I called it exam 3 and final or final, I'm sorry if that's confusing. I just think of it as 2 tests. One of the tests, and you could take that whenever you feel like taking. One of the tests is just as long as either of the earlier 2 exams, but it covers just newish material. Okay, so since chapter 8, 9. Okay, so think partial F test through the end of the term. 1 test on that. Okay, and then the other test, and if you want to call that a final, that's fine. That would be comprehensive. Okay, and comprehensive in such a way that we have equal level of attention applied to all of the different chunks of course material. So it's going to be more oriented towards which is the right method to use, and something along the lines of, do we maybe forget to do something within the t-test? You studied for it, but then, never hit a question on a particular subtopic, or big picture things. Okay. So basically think the final exam is comprehensive. Okay. With giving not so much emphasis to the most recent material. And then exam 3 is just covering that more recent batch of course material. Each of those tests is written to be a 50-minute exam, the same length as the exams you've seen so far, but you'll nominally have 75 minutes to do it instead of 50. And because I like to have you have a few minutes to upload your notes, let's call it a 50-minute exam where you've got 5 minutes to upload your notes. Well, if it was 75, 5 minutes, it gives you 80. So 80 minutes worth of time to do what I'll call a 50-minute exam, more time per question. Students don't run out of time on either exam 3 or on the final. Okay. So what else is different about those? Well, because there's more time per question, scores tend to go up. If you've been studying diligently or even semi-diligently, the score on the final exam should be higher. And that causes me to say your scores, as you look at them so far, according to our course weightings, if you will, the labs, homeworks, exam 1, exam, et cetera. If you are giving equal weight to all of the course components that we've looked at so far, and that's about the first 4 rows of these 5 rows, you will probably be giving more weight to exams that are harder than to the exam which we haven't done yet, which is a little on the easier side. Yes, I'm a statistician. I have done some analyses in the past to predict grades on the final exam based on exam 1, exam 2, and homework scores. Yeah. And interestingly enough, I could probably, if you have a question about where you're at score-wise, I could give you that forecast. I could say, well, someone like you with exam 1 and exam 2 scores and these set of homework scores, probably on the final, you'd be batting about 78%. And you'd be thinking, but I've been only getting about 70% on the exam so far. How are you expecting me to do better? It's because of a variety of factors. You know what the material better. 1, 2, more time per question. 3, you guys tend to do better, period, on that final than our earlier portions of the course material. So if you're wondering about where you're likely to end up term-wise, I could give you predictions. Just pop by office hours or send me an email and I'll be able to get back to you with, well, I bet on this score for you overall in the class. Okay, so that's a little bit of wrapping the weeks together, both content, here's what we're going to be doing, and then administrative sort of questions that usually come up at this point in time in the term. Do any of you have questions on administrative matters or what's going to be happening this week?
So you said exam 3 will be partial F test to whatever we covered this week?
Yes.
Okay.
Yeah. Basically, I write a final exam the way I normally write it, but because I think everyone deserves a break. Yeah, 1. 2, because I think that in a 5-week summer term, it's a lot easier to say, okay, here is one chunk of material and focus on that, make sure you're studied up on that, and then everything else on a separate exam. So that just makes it easier, Anthony, to sort of time the taking of exams to correspond to what you think you know and when you think you know it. It'll be due on Friday of this week at 11:59, but 2 separate things that are each nominally an hour and a half, and then give yourself a break in between them. I mean, that's all to work, but I know you can get it done. Anyone else want to ask an administrative question of sorts? Okay, so what I'd love to do then is to get into newish material and boom, that we'll do it then. So quantitative categorical variables. I probably shouldn't have phrased it that way, but quantitative fits for numeric factors. Okay. As an example, maybe I should show you this new data set, which I just finished downloading. I thought it was sort of cool, so maybe it's a good example. Here we've got data on the amylase activity in corn, and let me make sure I repeating this correctly for you. Darn it, the wrong website is open. Not that one. And you know what? I wonder if it's buried under all these other things. Okay, yes, finally found it. We're germinating these corn and we're looking at the amylase specific activity in these sprouted corns. 32 different treatment conditions. That's a lot. We're going to maybe oversimplify things here. Just know that that's the response variable and it is clearly numeric. There are growth temperatures of the corn. So the corn is either growing at 25 or 13 degrees centigrade. That seems on the warmer side. Okay, so that's the temperature at which the sprouts are growing. Then variety, and there's varieties 1 and 2. That's not so exciting. Temperature here, these are temperatures with literally 8 levels, 40, 30, 25, 20, 15, etc. Okay, so if I'm showing you this temperature, that is something that I'm going to call quantitative. Okay, and it's quantitative, and you could view these temperatures as literally numbers. In the past, so far, we said, because it corresponds to a treatment level, let's give it a categorical fit. And so let's maybe make these guys categorical for temperature, the temperature of growth and the variety and amylase activity. Let's just go ahead and maybe explore it graphically a little bit. And amylase activity on the y-axis. I think there's really a lot of different temperatures, and you could call them basically 10 through 40 degrees or something like that. And then that goes in steps of 5 degrees. And that would be Fahrenheit or centigrade temperature of the extraction process of the amylase. And we've got 2 different varieties, and you can see blues and reds are a little bit different. So variety matters. Maybe let's make this bigger so we can see it more easily. Variety seems to definitely matter. So if I show you different patterns, you'd say a blue is higher than red. Okay. The temperature of the growth, well, that's a little bit more diffuse, but maybe it matters. You think maybe a blocking variable here. And so really, why amylase activity depends on probably the variety, maybe the growth temperature, certainly the temperature. We can see that. And rather than having categorical fits like we've done so far, we're saying, how about we have sort of a curve here, a polynomial of sorts. Okay, maybe if we fit a curve, and this definitely doesn't look linear. And because it's both quantitatively going upwards from temperatures 1, 2 to 3, and maybe even 4, it's going up, up, up. And then it goes down. It's, if you will, non-monotonic. That's what mathy people would say. Oh, it's not just going up or not just going down. If you have something that's non-monotonic in its X-Y relationship, that Y sometimes increases as X increases, and sometimes Y decreases as X increases. In situations like that, you really can't, by a transformation, fix this non-linear trend and make it a linear trend. We would have to model that trend a little bit differently. And we've already hinted that rather than fitting a straight line, maybe I could fit a polynomial. Okay. So diving in a little bit deeper, and I'm going to use fit y by x for the moment because temperature, okay, and shoot, I'm going to make temperature quantitative right now. Continues. If we were to then under fit y by x, say that temperature may be used to predict the amylase activity, I could click OK, and you see this scatter plot here. And this is, of course, completely ignoring the other variables that we do think matter, like variety and possibly growth temp. But overall, if I fit a linear trend line, you're thinking, that's not so good. I mean, literally that downwards trend with temperature, it may be reflecting the average linear trend across the temperatures that we have, but it certainly doesn't match what's going on in the first 3 temperatures at all, which is a positive trend. And then if we were trying to model, temperatures 3 through 8, that'd be maybe linear but negative. There's clearly a problem. You might have noticed earlier this term, you could fit a polynomial. Hey, let's fit a quadratic. And that seems great to me, except for it seems like it's gonna predict for temperature 8, maybe a little bit lower than things really are in temperature 8's situation. And in that same sense, for temperature 3, the data points are above this polynomial, this quadratic trend line. The quadratic maybe isn't the best. Some of you might be saying, well, why not a cubic? A cubic seems to be better, and a cubic does, Blue, fit better. It sort of goes up, like the data seems to go up, then it goes down. But I'm spotting here in the cubic a sense of curvature that makes me uncomfortable to say, well, what if I tried not just through 40 degrees, but what if I tried 50 degrees over here? This cubic model would be a very poor choice. I think maybe a linear trend down for the recent temperatures would make sense, but this cubic, not so much. And in that same sense, if the temperature we were to try a lower temperature, each of these 3 models would dramatically differently predict something for a temperature level below the lowest one we had utilized. Again, 10 degrees centigrade. Okay. What if we're trying 5 degrees centigrade? You would say, oh, I don't know which one is best. Green, maybe? Well, clearly there are some other possibilities. Let's try another. Let's go for a 4th order polynomial quad. No. Okay, well, maybe is that better? No, maybe fifth polynomial. Let's go for a 5. Okay, so for 5, we get this different color of green, and it's like going way down, whereas the previous one, the 4th order, went way up. I'm spotting a lot of possibilities here, but the more flexible I make my model, the polynomial, if I fit a 6th order polynomial, it can't fit worse than the 5th order. It might fit a little bit better somewhere. What does it look like? Well, it's that purpley one, and I like the color purple, so I'm gonna say it's better than the others, but even so, it's gonna poorly predict for a temperature above 40 degrees centigrade. I think there's probably a linear trend, and none of the models that I fit would nicely tackle that linear. What can I do? What should I do with data like this? Okay, so let's get into the nature of how we're going to spot things. And I'll just claim for a level K, a K-level quantitative factor with different levels, K distinct levels of temperature, maybe 8 here, we could use a K-1 order polynomial to get the exact same fit for those K levels. I want to switch gears here and sort of draw some pictures for a little bit. If I remember from geometry, 2 points determine a straight line, or at least that's what they told me in the geometry class. And so if I have 2 points, and let's go ahead and draw 2 points in a trend line, and I'm thinking something like an experiment where there's two different levels of X. There's the low and then the X high value, XH for high. And I could have a categorical fit. And conceptually, if I'm saying, aha, there's just these two groups, there's a grand mean, and then there's an alpha for each of the groups. There's alpha L and alpha H. How much does the low differ from the average, and how much does the high differ from the average? And I'm realizing now I'm looking at an iPad where I can see it just fine, and I'm looking at my computer screen and I can just see that fine. But I don't know if any of you are in the sun or, bad lighting. Can you see the yellow? Are any of you unable to see the yellow and want me to switch to a different color? So far, so good. Okay. And whoever, I saw something flash by, but it looked like a thumbs up. Okay, so I'm good with these two different levels. However, if I wanted to, I could also fit a trend line through the values. And what I've chosen to show you here was, if you will, mu H, and then there's mu L. Okay, and then there's the grand mean, or if you will, the mean across the different treatment groups, mu. So we've parameterized things in a couple different times. There's like the average, period. And just think the average amylase level, okay? And there's how far are you away from average if you're in the low group, the low temperature group, or what if you're in the high temperature group? So I could have two distinct fitted values with the categorical way of thinking about things, the ANOVA way of thinking about things. But for the data that I have, I could also have an intercept beta 0, and there's a slope beta 1 out there, such that that slope beta 1 here will give me the exact same fit to those particular X's and their corresponding level of Y. So think one slope, okay, one slope, a linear trend, if you will, corresponds to two levels. I want to sort of erase some of this and move on. I'm going to erase the part that is over here off to the left. Dude, I'm probably erasing more than I need to, but what the heck, why not? Okay, so let's go back to our abscissa and ordinate. Oh, let's use a pen and go back to an abscissa and ordinate. And what if I've got three X levels, X low, XM, and X, well, let's even put it over here, XH, the high level for X. And I'm going to go ahead and erase that guy because they don't have to be evenly spaced. They're just three distinct X levels. And if we have, and I'm going to try and draw something like maybe what our data looked like for the low, the medium, and the high levels of X, we've got three distinct average values for Y. These are Y bar for XL, Y bar for XM, and Y bar for XH. If I were to then view this as like an ANOVA, I have, if you will, the grand mean. Okay, so that's mu. And then there's alpha for L, alpha for M, and alpha for high. One low, one medium, and one high effect. How different are you from the average amylase level for the low, the medium, and high temperature? Well, shoot, no problem there. But I can't, with one linear trend line, match up to all three distinct levels. But if you remember from that geometry class in high school, or it might have been algebra 2 also in high school, there is a unique parabola that goes through all three of these X levels, where Y is a function of X and a function of X squared as well. So I'm going to try and draw a parabola, and I'm always craptastic at drawing parabolas. So Okay, you know what I'm trying to do. Okay, so let's just write it out this way. 3 levels, okay, is going to correspond to, well, a quantitative slope and a quantitative slope for a quadratic term. Let's go with a quadratic. And the quadratic model looks like beta 0 plus beta 1 times x plus beta 2 times x squared. Okay, quadratic. And in that same sense, if I were to have 4 distinct levels of x, I could either have a mu and 4 different alphas that sub to 0, of course, or I could have a cubic model and I would do just exactly the same. So any questions about like 2 points from a line or 3 points will get you a parabola? Any questions about the concept? Okay. Screw that. Come on. Okay, and now back to where we were before. So essentially, if I've got k levels of my quantitative factor, I could do a polynomial of order k minus 1. Now, the example we gave you earlier is a little bit complex for that, with 1, 2, 3, 4, 5, 6, 7, 8 different distinct levels. I'm not going to start there with that example. We'll get back to this one in a little bit. But I want to start with something that's simpler, not similar, simpler. Okay, so here's an entirely made up data set, but I didn't make it up, so I can't be blamed. I've got temperature levels of 50, 70, 80, 90, and 100. So that's 1, 2, 3, 4, 5 different levels. The claim is a polynomial that's of a 4th order will fit these data perfectly. So I'm going to try this 2 different ways. And I'm going to try temperature as categorical. And with our friendly fit model, we're going to say the yield is depending on which of the 5, I'm sorry, 1, 2, 3, 4, which of the 5 levels of temperature we're utilizing. And our fits, I guess I could save those. I will in a second. But here are our friends, R square, the F for the model, and parameter estimates. And the parameter estimates here, well, maybe I'll make even a picture of this. Graph builder. Let's look at the shape here. Yield may depend on the temperature. That doesn't look linear. It really doesn't. It might be quadratic, but I think it's not quadratic because it would have to bend down a little bit to fit that highest temperature. So I get the feeling that I could say that the average yield overall is 2.83. But if the temperature is 50, you have the yield being a little higher. If it's 70, it's a lot lower, 80 lower, 90 a little higher. And then that temperature 100, let's go with our under estimates, expanded estimates. And so you can see the effect of the temperature being 100 is to have a considerably higher yield than the other temperature yields are. Okay, so that's my categorical fit. But I could, by taking temperature and making it quantitative again, I could go ahead and fit a model. And we claimed then that yield would be the equivalent of a temperature. Well, one of these things is a polynomial up to degree. We said we've got 5 levels of temperature. Let's go with polynomial up to degree 4. So under macros, we get polynomial to degree 4, temperature squared, temperature cubed, temperature to the 4th power. Okay. Now I'm going to say the way our textbook would choose to do this, if you want your results in JMP to match the author's style, you would want to deselect the center polynomials. Here, I don't care. In fact, here I actually even prefer to have the polynomials uncentered because it reduces the multi-collinearity problem that we have across multiple x's. So I don't like to deselect the center polynomials for this sort of an analysis. So let's go ahead and run it. Now, the thing that I do like about the fit model with this quantitative version is it draws in that stinking picture. Oh, well, here's your picture of what we just fit. Now, what we just fit is, well, literally just the average yield when the temperature was 50, the average when it's 70, 80, 90, and 100, but I happen to have a curve drawn in because the model we're fitting is literally a curve, but looking more carefully, our squareds are the same. Root mean square error, the same. Mean of the response, that's the same. Let's get the ANOVA for the model is the same. On the exam, one of the questions I asked you is, hey, what if you have these two separate analyses that look dramatically different? Could they actually be the same? And if the fitted values are identical, they are the same analysis. So let's go ahead and save those two fitted values. I'm going to save those two predicted values in the fit model. And here under our, I could say columns are predicted values. Now looking at our columns of our predicted yields via the quantitative fit, they're the exact same as the predicted yields for the categorical fit. The quantitative fits and the categorical fits are the same. So which is better? It's actually not obvious to me that there is one that is better than the other. They're the same, but I would suggest, depending on what you want to do next, there may be a benefit of the quantitative way of describing the relationship between yield and temperature. Let me tell you I'll tell you three things that could be portrayed as a benefit, and I'll tell you why one of them really isn't. And then we'll focus on that third one. First, I, with this trend line now, could interpolate and say, well, what if the temperature was 75? Do I have a way of predicting what the yield would be? I do. Over here in my 1, 2, 3, 4, 5 different category groups, do I have a way of telling you what I would expect the yield would be if it was 75? You'd think, well, the effect would be somewhere between -0.5 and -2.33, probably, but you don't know exactly where it would be. Here we have an estimate of where it would be. Interpolation, benefit one. Benefit two, and this is not really much of a benefit, but if I were wanting to extrapolate a little bit, we could. I would personally feel a little uncomfortable extrapolating very far out at all because I have this quartic model. It's not just x squared, x cubed. I've got an x to the fourth in there. And so that means this is going to be dropping, plummeting like a rock very soon, or climbing very quickly for temperatures above 100. Similarly, for temperatures below 50, it's going to bend down right quick or sort of skyrocket. I don't know which it is exactly. Okay. I have a suspicion it's going to be bending down, and I'm suspicion that one is bending down as well because it's quadratic or fourth order. So that means it should be going down at both ends together. Mathy nerd stuff. Okay. So I'm going to say we'll go down at both ends, and that's not very much matching the pattern we see of below 50. I would expect the temperature actually would probably be a little higher. I mean, give me a higher yield. And if the temperature were above 100, I wouldn't expect it to be plummeting. So I like the interpolation, the extrapolation, not so much. What is another benefit of this complex fourth order polynomial model? And that is found not in the effects test, but rather in my sequential tests. Let me look at my, not the parameter estimates. Let's look at the sequential test, and because that's way low for me, I'm going to sort of get rid of that. And so I can, darn it. Okay, so I'm going to just move it up here, and I'm going to read, well, there we go. And there we go. And maybe I want to see the picture at least. I don't even know what I'm doing here. Okay, the regression plot I want to see. Okay, so the way I would read these sequential tests are controlling for previous variables. Does this one beat the previous model? And so compared to a model without temperature in it at all, does having a slope for temperature seem to allow us to do better? Is there a general temperature slope? We're saying we're not really sure yet. Okay, it looks like it to me over here, but that's a downwards, and so I'm saying, I don't know. But compared to a linear model with a temperature trend overall, does adding in a quadratic help me do better than a linear temperature trend? And we're saying here, yes, quadratic is better. Above and beyond a quadratic model, would fitting a cubic allow me to do a better job? Maybe. I'm not really convinced of it just yet, but maybe. What about above and beyond the quality of a cubic fit? Does having a fourth order temperature help me? I don't see any benefit of a fourth order model at all. So I'm going to go ahead and set myself up for the next thing. And under analysis of variance, I want to leave that on the screen for my quadratic, my fourth order polynomial. Maybe I'm trying to get these side by side in just the right way. Okay, so my categorical fit, my my fifth degree polynomial, or fourth order, x to the fourth power, temperature squared, temperature cubed, temperature to the fourth power, same analyses. But I'm saying I don't know that I really need this last term, temperature to the power 4. I don't know that I need it. Let's go ahead and reanalyze our model, fit a new model. Just the same as before, except for that last term, which the sequential sum square says you don't need this one. I'm going to delete it. I don't need it. Delete it. So we're fitting here a cubic polynomial instead of to the fourth order. Okay. The picture isn't dramatically differing than before. My regression plot is, yeah, it looks about the same. So we can see that, yeah, that greater complexity over here versus here is not dramatically better. Maybe for my summary, the fit 73% of the variability of y is explained by x. What about now? It's 70, instead of 73.56, it's 73.55. Pretty clear there's no real benefit of having the more complex than the less complex model. Okay. So our model is about the same, and I wanted to do that. There we go. And my two fits so far. Let's contrast them with my analysis of variance, my ANOVA for this new model overall. These are both an F ratio of 7. Now it's at like 10. What happened? What's different really seems to be we took our model, which had 4 degrees of freedom attached to it. We reduced it to a cubic model from a quartic. It became, well, fewer degrees of freedom for the model, but about the same sums of squares as the model has, resulting in a mean score which is higher. Similarly, for error, the error was sum of squares of like 0.58. Okay, it still is about a 0.58, but a hair larger. But I've got 11 degrees of freedom for error. So my mean square error is a little bit lower. We've taken our model, which was noticeably significant, but we're now saying, you can even better have a higher F ratio because of the reduction in unnecessary complexity. The categorical version of the model says, oh yeah, there is a difference across the groups. We're still saying there's a difference across the groups that's noticeable here. But I would suggest the following. If you were in a situation where you could barely spot a difference across the groups, maybe not even spot a difference across the groups, if you fit a polynomial as appropriate, that appropriately fit polynomial will allow you to better spot the real trend. You're more likely to spot the truth if you use this polynomial fitting approach. Quantitative factors, numeric factors, as long as you treat them like polynomials, you're better off. That is the lesson I'm trying to suggest. Okay, so let's, any questions first?
Why would you not?
Okay. Go ahead, please.
Why would you not take out the x to the cubed one? Because it's not significant either.
You're right, I could, and I don't want to dwell on this example, but rather want to look at the amylase activity example, where I think it's even more interesting, I would claim. Yeah, okay, because it's real data, it's more interesting. I don't know, but we'll find out what the results are. I've never done this analysis before in my life. But again, under Graph Builder, we said the amylase activity may be a function of the temperatures, which we could fit as a quantitative variable. And we know variety seems to matter, so we're going to have to include that in our model. But the question is, blue and red, do they seem parallel? They do seem parallel to me, approximately parallel. And could I go ahead and fit a model that this one implies? I think I can. So over here is my amylase activity, and let's go ahead and fit that model. Okay, well, just to convince you that it's true yet again, I'm going to take temperature and say it's just a category that you're from. I'm going to do my analysis the way we suggested, that the amylase activity may depend on the variety, blocking variable of the growth temp. I don't know if it'll matter, the temperature itself. And I'm not considering interactions here. I don't believe this data set will need any, but you know, some of you might have been wondering, what about an interaction? I don't see a need for one just yet. If I fit this analysis and determine, oh, hold on, by a look at the scatter plot of the residuals against the different X's, I might see a need for an interaction, but I don't see one just yet. Okay, so I'm going to run that analysis, and I have a I have an R squared of 86%. I'm able to explain 86% of the variability. There are my parameter estimates, the effects test. Just forget the effects test. But it does look as though these different temperatures, okay, result of where we process things, result in different levels of amylase, okay? And this temperature 8 might also be different from the average amylase level, amylase activity level. But because I've got 8 distinct levels, if I want to fit this as a 7th order polynomial, that should be identical. So let's go ahead and try that fit model, and temperature we're going to now treat as numeric or continuous. I'm going to hit recall, but temperature, remember, because I don't want to fit just a linear version of temperature, I'm going to say, well, I've got 8 levels, a 7th order polynomial of temperature, that thing over here off to the left. We're going to apply the macro to it, and it's a polynomial up to degree 7. So temperature, temperature squared, temperature cubed, the 4th, the 5th, the 6th, and the 7th. Okay, well. I guess I could make that bigger, and you could see that is to the 7th power. Go ahead and run that analysis. And well, it's not showing me the picture of the model itself, because the 7th order polynomial is sort of a pain to deal with. It doesn't realize that that is the same. Okay. And the residuals by predicteds, maybe a lack of equality spread, maybe a little bit less variability here than here, but I don't know for sure. We'd have to be more careful. Same R squared as before. And as we suggested, my under estimates, my sequential tests might allow me to tackle some problems of interest. And one of those problems is, do we really need that 7th order, temperature to the power 7? I'm going to say no. And controlling for temperature, I mean, sort of controlling for a model with temperature to the 6th power, do we need temperature to the 7th? No. Do you need temperature to the 6th power? It doesn't look as though you do. It doesn't beat a model with temperature to the 5th. Does temperature to the 5th beat a model with temperature to the 4th? Not really. Does temperature to the 4th beat a model with even temperature cubed? The temperature cube model is pretty darn good here, but 5th, 6th, 7th, 8th, we don't spot a difference or a benefit of any of those. Yeah. Would I be happy with a polynomial of the 4th order, temperature all the way through the 4th power? I'm sorry, temperature through temperature cubed and not need 4th through 7th? Yeah. Now I'm going to sort of jump whole hog to the very end then. Recall that? I claimed that we only needed through temperature cubed. That was a guess based on my earlier analysis. Okay. We don't know what would happen if we tried a partial F test for temperature to the 4th, temperature to the 5th, temperature to the 6th, and temperature to the 7th power. We don't know. It's entirely possible that across one of those last four rows, one of them would have been very helpful. Again, the sequential sums of squares, you know, across those 1, 2, 3, 4, maybe across the 4 of them, they would add up to be impactful enough that there would be an F ratio that I would notice. I don't think so here. But if I were to run our quartic model, temperature through the 4th power is being utilized. We can spot still R squared is about the same as what it was before. We had about an 85.5%. Now here it's instead of 85.5%, it's 85.0%. Not dramatically different. But spot here that if we got rid of those excess parameters in our ANOVA, instead of an F ratio of 56 overall, we're now with an F ratio of 101. Again, these degrees of freedom, when we put them into error instead of our model, we're now with fewer degrees of freedom for the model, more degrees of freedom for error, but the sum of squared errors remain about the same. Sum of squares model remains about the same. Our mean square for the model goes up. The mean square for the error drops, not much, but a little bit. And because of that, we get a higher F ratio. So that is another benefit of this polynomial way of characterizing things. Interpolate, yes. Yeah, don't really care if we can extrapolate, but the big one is this. If we use fewer degrees of freedom for the polynomial trend, because of we can eliminate those higher order polynomials, we can be more likely to spot something that really does matter. Okay. We talked about before the temperature. Does it matter? under effects test, does temperature, well, no, let's go for the parameter estimates. It's really hard to read this one. Does temperature have a p-value that matters? Okay, so it's the one growth temperature to 0.2244 as the p-value for temperature or growth temperature. Now it's 0.2230. It's a hair lower. Similarly, our okay, well, let's just go with that. I'll just say it's a hair better. This is not a super convincing example of, oh, look, we could spot something here that we couldn't have seen before with the categorical way of fitting things. But this is a real benefit, and it will, from time to time, reveal something which otherwise would not have been revealed. Okay, good place to stop for the day. The lab activity is one with Cal Poly data. Any of you in animal science? Okay, so Bill Plummer, emeritus in animal science, collected those data with some students a while ago and was looking again at path versus control, fresh versus cooled, and the motility across time. You're looking at those data today and trying the categorical versus the polynomial fits and see how well you do. I'm going to stop the share, and any questions before I turn off the recording? Okay, so enjoy the rest of your day, and we'll see you tomorrow when we will pick up with Q&A that you might have on this, but also which variables should I pick for my analysis? To be honest, if we have 50 different possible variables to include or not, trying to figure out which ones we should include is going to be a challenge, and it's a challenge that we want to handle carefully. So that's chapter 11 tomorrow, but we'll see you then. Bye-bye.